All right, so now I want to return to the problem we started off with, the fact that we had this here. So we saw that we have, in this case, x plus 2, and 35 minus x here. We were able to solve this. We get LM is 22 here. So we know that in this situation, LM is 22, and we each have two segments of length 11 here. So that's no accident, right? If you think about what a midpoint does, it splits its segment into two congruent pieces. And those two congruent pieces are going to add up to the whole here. So it would make sense. So this is one equation we could have written. But another equation we could have written here was the fact that LK, this x minus 2, we could have also written here that LK, right? Another equation we could have written was LK here was 1/2 of LM. So we can say that x minus 2 is 1/2 of 35 minus x. And you'll note that if you try setting it up here and solve this equation, you should get x equals 13 yet again, right? Just to be on the safe side, let's go ahead and do that. So we get 35 over 2 minus x over 2 here. So I can multiply everything by 2 to get rid of the fraction. So 2x minus 4 equals 35 minus x here. And again, this transposes right back here. So note that we have an equation that's very similar to this one here. So this leads us to one of the first theorems that we're going to be looking at here. So in this situation, we can do something like this. So we can say, for instance, here that the midpoint of a line segment, the midpoint of a line segment here, we'll divide that segment into segments half as long as the original here. So notice how in this situation here, this is actually, even though it seems kind of obvious to us, this is something that we can actually prove. This is a statement that we can use our tools to prove here. So let's set this up. As always, we want to set up what's going on here and see what's happening. So let's see what information we have here. So notice that we have the midpoint of a line segment. They gave us that, and we have this picture to start us off here. So it makes sense for us to start off with the fact that M is a midpoint. And we can say that that's going to be our given. M is the midpoint of AB here. So notice that the statement, it does feel like you were given the fact, it does feel like, you know, at the beginning you were told that you have a midpoint of a line segment here. In general, when you're trying to prove theorems here, a lot of the information that you're going to be starting off with will start off in the first half of the statement here. And we see that it divides that segment into two segments half as long as the original. So that means what we're attempting to do is we want to show that the two segments are each half as long as the original. So in this case, AM and MB should be 1/2 of AB. So notice that, in fact, here, our setup requires two statements here. We're going to prove, we're going to show that, in this case, both of these are true here. We're going to try to set this up. So let's go ahead and figure this one out here, okay? Maybe we can see what we can come up with. All right, so let's go ahead and set this up. Note that in this situation we're given this here. Doesn't really help us out too much, but consider this. So we're actually going to go ahead and write this proof out together here. And I actually highly suggest that you pause the video right now and see if you can figure out sort of the general idea about what's going on. What can we do here? Okay. So in this situation here, notice that we have AB, which is going to be one piece of what we need here. And we have AM and MB. So we'd like to have statements that involve AB and also AM and MB. An obvious statement that pops up is that fact that AB equals AM plus MB here. That's going to be our partition postulate, if you recall. So we can use our partition postulate here to get that, and then we can do a little bit of finagling here, because we know M is the midpoint of AB, we know AM and MB should be congruent, so they have equal measure. So we can kind of do a little bit of finagling here. So let's give this a go. We're going to give this a try here. So as always, we're going to start off with our given. In this case, M is the midpoint of AB. And that is given to us. Okay, that seems pretty fair. Now, note midpoint is a term that we defined before, so we can actually just simply use the definition here, right? We know that according to one of our previous definitions from a couple days ago, we saw that a midpoint divides a segment into two congruent segments. So if we follow the definition to the letter, we know that AM is congruent to MB here, right? And that we can explain by utilizing the definition here. Because a definition is a perfectly valid reason here, I can simply say definition of midpoints. And that's from step 1 here. Now, it probably would be more proper if you wrote out that a midpoint divides a segment into two congruent segments here, but we can simply use the midpoint that way. Now, that's all great. This is wonderful. Now, unfortunately, we have a bit of a problem here. Notice how this statement says AM is congruent to MB here, but my goal has equality, and there's no congruence here, it's equality. So we have to, we're stuck in the realm of congruence. We need to somehow move into the realm of equality here. And note that we can do that by our definition of congruence. We know that congruent segments have equal measure here. So the next statement here will be AM equals MB here. And that's going to be our definition of equality. Normally, so ladies and gentlemen, I want to mention this here, and I want to be really specific about this. Normally, we're going to stay in one dimension or in one realm or another, the realm of congruence or the realm of equality. There are very little times where we're actually going to switch between the two realms here. But in this situation, we have to, because the definition tells us a congruence here, whereas our goal says everything with equality here. So that's what we're going to have to do. That's why I had to do this here. That's why step 3 is necessary, so that I can convert, cross over from congruence to equality here. Okay, now, considering that we know that AB equals AM plus MB, that's probably a good idea for us to introduce next. So we can write that in this situation, AM plus MB equals AB here, and that's our good old partition postulate. Right? So again, note it's a postulate here. You don't have to explain why it's true, because it's true. It's a postulate. So notice now in this situation here, what we can do is we can do this, right? So notice that AM and MB here, our goal is to show AM is equal to 1/2 of AB. So AM here, I'd like to get rid of the MB somehow. Luckily, we know from step 3, MB and AM are the same. So I can substitute. So I can write AM plus AM equals AB here. And notice that in this situation, now I can actually swap this up. I can write that 2 times AM equals AB here. I'm just doing this here to show that we're doing a calculation. So in this case here, this is going to be our substitution postulate. And that's going to be from steps 3 and 4. We're subbing 3 into 4 here, right? This AM equals MB gets substituted into this statement here, right? We can get rid of the MB and replace it with AM, right? So these two things match, so I can get rid of the MB and replace it with AM. Now, this is not our goal, but we're pretty close to our goal, right? 2AM equals AB. So what I have to do to get to 1/2 AB is divide both sides by 2. So in order to use a division postulate, we want to make sure that we can divide by 2 here. So remember that the division postulate works just like the addition and subtraction postulate. You need 2 pairs of equal things, in this case, we need 2 pairs of equal things. I've got one pair, but I need another pair. And that other pair we know is going to be the fact that 2, right? We're going to divide both sides by 2. And we can establish the fact 2 equals 2, and this is our reflexive property here. And now we can actually do our division postulate. So now we can divide everything by 2 here. So 2 times AM, we can now divide this by 2. So 2 AM over 2 is just 2. And then AB divided by 2 is 1/2 AB. And that's our division postulate. And that's 5 and 6 here, right? We can see we use our division postulate on steps 5 and 6. It works out really, really well. Wait a minute, it's only half our goal, right? We also have to show MB is half of AB. But that's actually not so bad, because notice that, again, we've established the fact that AM is equal to MB here. So now we can swap that out. We can say MB is 1/2 of AB here. All we're doing is a substitution from there. This is going to be our substitution postulate. And notice that we're substituting 3 into 7 this time. So in this situation, notice how step 3 is actually used multiple times in the proof here. Usually that doesn't happen. Up to now, we never really had that happen. But now, we're going to see that's okay. There's nothing wrong with using steps multiple times if you need to. In this case, we needed to here, and it worked out really well. So notice that this is a theorem here. We were able to prove that this statement is always true, considering the information that we had here. We had all this. We were able to prove this to be true. So this is a theorem. And now, if we want to invoke this theorem, we can just simply mention this theorem by name. So instead of going through all this here, we don't have to keep reinventing the wheel. If we are given the fact that M is the midpoint of AB as a given, I can now state as a statement here that AM is half of AB because of this theorem. The midpoint of a line segment divides that segment to 2 segments half as long as the original. So now you can think this is a new sort of law here. It's a quasi-law in a way. It's something that we now know is true, so we can invoke that as a reason. And you're going to see that we're actually going to do this in future examples here. In one of the future examples, we're going to see that this is going to be something we'll use. Okay? Now, note that this works for midpoints here, but this also works for angles as well, right? So for instance, we have the fact that we can also mention the fact that we have an angle bisector here, right? So if I've got an angle like so, if you recall, we mentioned this idea of angles here. So our angles like this here, right? We can mention this. So remember that with an angle, you want to make sure that you have these 2 rays that are joined by a point here. And we talk about the measurement of angles in degrees here, right? We talk about what it means to be an angle. The angles are measured in degrees, and of course we have our terms for angles. We have acute angles, right? Where let's call the angle, so let's call the measure equal to x, right? So acute angles are going to be between 0 and 90 here. So notice it's going to be strict inequalities here. We don't want to include 90 because 90 is for a right angle. We have our right angles where x is 90 degrees, right? We have our obtuse angles here where x is between 90 and 180 here, right? We want to mention that. We also have our good old straight angles here where x is 180, right? Because we can have two right angles together to create a straight line, that's 180. And then we can also have our bigger angles, which we call reflex. So 180 is less than x is less than 360 here. Okay, so just different categorizations of angles. Now note here with the bisector of an angle, it divides that angle into two, so it looks something like this here. It divides the angle into two congruent angles here. So note that the definition of an angle bisector is actually a little bit different from the definition of a segment bisector. The definition of a segment bisector requires you to go through the midpoint first, but here this doesn't make, there's no such thing as a midpoint of an angle here. So we actually just focus on this here. So from the definition of angle bisector, we can say that angle ABD and angle CBD are congruent here. And indeed, we can create an analogous theorem to what we had before, where the bisector of an angle divides that angle into two angles, each half the measure of the original. And this is something you're actually going to investigate. That's actually going to be the first half of the homework here. You're going to be able to show that this is going to be true using a method very similar to what we just did here. So I would suggest that you rewatch this video and review what we did here, because you're going to be doing something very similar for the next thing.